Hello. Thank you very much for being here today. My name is Athanasios Douitsis. I work for the National Technical University of Athens Network Operations Center, and I'm here to tell you about a couple of projects that I've been working on for the last 2 years and are related with the assignment of persistent IPv6 addresses in broadband access networks. So, here's how we will proceed. I'm going to go basically through two separate case studies. The first case study is about the Greek student network, and the second case study is about the Greek school network. On both of those cases, I'm going to briefly describe the previous IPv6 setup, and then I'm going to describe the work that we've done or we are doing at this point. Most of what you're going to hear has already been implemented. A good portion of it is already in production, and another good portion of it is moving fast towards production. So, we're going to conclude with some remarks and some best practices that we've come up with. But before we proceed, just a trifle of orientation. I'm going to be referring to broadband access networks where the user is connected to a home Ethernet LAN, which is connected to a CPE. The CPE establishes a point-to-point link to an aggregator, an LNS if you like, which communicates with a radio server. The point-to-point link is enumerated as usual with stateless address auto-configuration. And then the home LAN is enumerated with the IPv6 prefix delegation. The IPv6 prefix that goes to the point-to-point link comes from the radius via the framed IPv6 prefix radius attribute, ITF radius attribute, and then the IPv6 prefix that goes to that enumerates the home LAN. Then the home LAN is enumerated with a prefix that comes from the delegated IPv6 prefix radius AV pair. So basically, in this setup that I'm describing, you can see that there are no local pools on the aggregator. This means that the configuration of the aggregator is rather simple, no local pools, which is basically a vendor-dependent solution. But obviously, this means that your radius must be a little bit smarter, especially in the case where you have multiple LNSs, but not too much smarter. So, on to the first case study, which is about the Greek student network. The Greek student network is basically a network that provides net connectivity to university students throughout Greece. The Greek student network is operated by the Greek Research Network. We have like 50 institutions involved. At this point, we have like 50,000 or more students. We do our own IPv6 and IPv4 address assignment, but we outsource all the user billing and all the front-facing and the registration to a couple of commercial ISPs, which incidentally do the authentication. So our proxy radius does the IPv4 and IPv6 address assignment, but then proxies the authentication, proxies the authentication request to a couple of home radiuses belonging to the commercial ISPs, which has some peculiar ramifications because since the user databases are on the ISPs, the account usernames are unknown to us until the time the users log in for the first time, and more so, the deleted accounts are unknown to us, and the time of their deletion is unknown. So when an account actually connects for the last time, we don't know whether this is actually the last time. So we have very limited view into our user database. So we had IPv6 from like 2009. Late 2009. This is how we used to do it. We were using an IPv4-based method, which means that since each time the user connects, the user gets a random IPv4 address from an IPv4 space. By calculating the relative position of the IPv4 address relative to the master IPv4 space, we can calculate an address offset, and then we can use that offset in reverse with two IPv6 prefixes to enumerate them, and come with the final framed IPv6 prefix and delegated IPv6 prefix. So this is simple and efficient, and it's stateless, because I mean, since you have the IPv4 address, you can come up with the IPv6 address without having to actually store anything. But of course, since each time the user connects, the IPv4 address changes, this means that also the IPv6 prefixes change. And you know, one of the constant requests that we've been getting from multiple sides was that people were asking for static prefixes per user. So we sat down and thought, how could we implement a static framed IPv6 prefix and a static delegated IPv6 prefix per user? Well, we thought we could just randomly choose two of a framed IPv6 prefix and a delegated IPv6 prefix per user, meaning that it's not deterministic from the username. The prefixes are not deterministic from the username. We'll just make that they always stay the same. They stay persistent across changes, across reloads, across whatever changes. And of course, at some point, we're going to run out of prefixes, obviously. So we need to come up with a way to, at some point, start to recycle our prefixes. So basically, here are the requirements, the detailed requirements we set out for ourselves. I'll go through them as fast as I can. Newly appearing usernames get assigned an IPv6 prefix on the fly. Subsequent logins of the same already seen username will always yield the same IPv6 prefix. Obviously, we'll try to retain the prefixes we have already assigned for as long as possible, and maybe we can even set up a guaranteed period, for example, 6 months, at least 6 months before a prefix becomes candidate for recycling. And we'll always try to recycle the least recently used prefix that we have. This whole process must work very fast because, as you can, from what I've described previously, this all happens on the fly during the AAA request. So we are actually bogging down the authentication request. So we need to come up with a sub-second response to this problem. And we obviously need to have a way to monitor performances with as detailed a way as possible. Obviously, I mean, maybe we'll have different subscriber groups drawing from different prefix pools. And of course, for law enforcement purposes and audit purposes, we'll need to have a way to log all the past actions that have happened, So here's our approach. For each user, we elect one unique static non-negative integer, which is the offset, and which we're gonna use in the same way that you used in the previous IPv6 setup that I've seen. We'll use this offset to enumerate the framed and the delegated prefixes. For example, if we have a pool size that has a size of 8096, we'll have to come up with offsets from 0 to 8095 to assign. When there's a new username appearing, if there's an unuser offset, then we'll create a new record with that username and offset pair. At some point, there will be no free offsets available. So at that point, we'll start always finding the record with the oldest offset, which is not in use. And then in that record, we'll replace the username. Of course, before we do that, we'll store the old username offset pair in some form of log. And of course, if there's an existing username, a username that we've seen before, we'll just retrieve the offset username pair and then return the offset. So basically, here's how it works. For an example, you have on the leftmost box, you have the delegated pool space from which all the users draw their prefixes. You have a stored offset for example, one user. And then on the rightmost box, you have the final delegated prefix, which is a /56. This means that we can have like 65,536 final delegated prefixes, and an equal amount of users. What's interesting is that all the prefixes, the non-negative integers, get stored in an ordinary relational database. And I mean, integers are very easy to sort them. It's very easy to sort integers. It's very easy to count integers. And there's an added benefit before. If at some point we need to do some sort of renumber or something similar, we'll just replace the delegated pool space on the leftmost box. And everything else is going to happen automatically. So this is an added benefit. It took me about a month to come up with an implementation for what I've just described. It's a Perl module that is actually integrated with a free radius server through the RLM Perl module. And as a storage, it uses a MySQL relational database. There are a couple of tables. There's the IPv6 prefix pool table, which will contain, you know, the master pools from which we draw the prefixes. There is the static addresses table, which contains the offsets and the usernames. And there are a couple of log tables for audit purposes, as I've described before. The entire code is, as you can see, available on my GitHub page. Some features which might be of interest is that, like I said, we have the ability to group our users into many different groups. We have the ability to keep track of our online users, and if we like, we can detect double logins and similar situations. We are able to configure a guaranteed inactive address retention, meaning that since you get assigned a prefix, you cannot lose it if you stay inactive for up to 5 months. After that period is elapsed, you don't automatically lose the prefix, but you lose it when your prefix becomes the least recently used. And lastly, we took all the care to make our system, so that our system can be operated by multiple radius daemons which operate on the same database. So we took all the extra care to implement all the locks and all the necessary features that we should do. So, like I said, we are very interested in monitoring the performance because, as I said, we are bogging down the AAA process. So we have we've taken extra care to implement all this performance counter inside our code. We can measure the average duration for each different case, create record, retrieve existing record, replace the offset in the record, log out. We keep counters for each of our different cases, and we even have drill down timers for each of our different types of SQL queries, SQL queries. So as you can see, we have a very, very detailed sense of where our system spends its time. So this system has been in production for almost 2 years now. It's very fast. Actually, the 50 millisecond amount is slightly exaggerated. I think most of the requests complete in less than 10 milliseconds. Initially, we had one and only initial master pool, but at this point, we have segregated our users into one big master pool, and some users are also located in a second address pool. So all in all, we're very happy with it. This is the second case study, and it's about the Greek school network. The Greek school network is a countrywide broadband access network in Greece that provides network access to almost 18,000 schools and administrative units belonging to the Ministry of Education in Greece. Apart from providing access, we have a very sophisticated content filtering system. We provide information services to schools and teachers, web hosting, email, everything. We have like more than 10,000 CPEs. We have, at this point, we have 6 router LNS aggregators. We have 2 radio servers and a multi-replica directory. We had IPv6 for 10 years now in the Greek school network. In fact, the Greek school network IPv6 setup is mentioned as a case study in the book from Cisco Press, Global IPv6 Strategies from Business Analysis to Operational Planning. So if you have the book, you might as well take a look at chapter 5, where I think we are mentioned. All the units used to get the prefixes from the same prefix pool, A /63 was assigned per unit, and it was split into a /64 for the point-to-point and a /64 for the IPv6 prefix delegation. The assignment of prefixes used to be semi-manual, and so it was, obviously an error-prone and cumbersome procedure. So, and one more thing, the IPv6 prefixes were stored as in the directory as verbatim IPv6 radius attributes, so as radius reply items for those of you who are more familiar with this type of AV pair. So basically we sat down and thought, let's design the IPv6 setup that we're going to have on the Greek school network for the next 10 years. So we'll try to design for the next 10 years ahead. This time we'll assign a static /56 per school, which means that each school or administrative unit will be able to enumerate a maximum of 256 VLANs. This time we're gonna store clear IPv6 prefixes in our directory, which is a more vendor-neutral solution. We're not storing VSAs in the directory. And this time we'll extend the directory schema with a couple of dedicated IPv6 attributes, which makes sense. And of course, if necessary, we'll have the radius translate to whatever VSAs we need to use, only if necessary. So this is a smarter setup. And this time we'll group our units into 3 categories: high schools, elementary schools, and administrative units, and we'll assign from different prefix pools per category. This is going to come very handy. This is going to become very handy in the case of policy enforcement and content filtering. As I've said, we have very sophisticated content filtering, and being able to enforce our policy is very important, as you can see, especially for the elementary category, which is full of underage minors. So we took extra care to make sure that we have all at least we're trying to make all the right choices in that regard. So about the IPv6 pool dimensioning, we'll assume that we'll have double the units in like 10 years, which is not going to happen. So I think we're pretty safe on that regard. For the directory services, for the directory, we are coming up with 2 new attributes. They're strings, and they are the framed IPv6 prefix and the delegated IPv6 prefix, as you might have guessed. And they're translated, obviously, by the radius to the framed IPv6 prefix radius attribute and the delegated IPv6 prefix. And there are some more AV pairs that we're still considering how are going to be generated or statically allocated. The goals that we set out for the software that we're going to be using is, obviously, the operation must be as automated as possible. We'd like to have 2 modes of operation. First, we'd like to have a batch mode of operation, which means go into the directory, get all the units, assign prefixes to every unit. And we'd also like to have a single unit mode, which means go to the directory, get that specific unit, assign prefix only to that specific unit. Obviously, like we had on the Greek student network, we very much like the ability to do on-the-fly renumbering without much hassle. And as you can probably imagine, the units are going to get created and deleted all the time. So we need to come up with a general way to have a sort of life cycle automation with the automatic detection of the creation and deletion of units. So the requirements for the software are pretty much obvious. Obviously, the software must be able to update the directory entries. Like I said, it must have multiple configurable groups and pools, and possibly with different delegated prefix length per group. And of course, it will have to be able to assign the framed and delegated prefixes per unit. The algorithm that we're using is pretty much the same with the Greek student network that I've described before, which means a new unit gets assigned a new free prefix, an existing unit always retains the same prefix, and a deleted unit causes the prefix to be recycled, and everything gets logged, of course. So here's the previous slide in more color. The big circle, the big orange circle on the left is our software. The software reads the units from the directory one by one, also reads the offsets from the pool an address offset DB. If there's a new unit, it creates a new offset in the DDB or recycles as necessary, classifies the unit to its category, gets a pool for the category, gets the offset for the unit, and then finally calculates the prefix from the offset. And then stores the result into the pair of directory attributes that I have shown you before. The software code, we were able to use a good portion of the code that we've written for the Greek student network. We were able to use it for the Greek school network, but this time this piece of software is standalone. So we had a considerable more leeway in order to make it more modern. We were able to use a modern version of Perl with all the new features that there are there on the syntax. We were able to use whatever CPAN modules we liked. Obviously, our software now can communicate with the database and the directory. And of course, we're using a modern version of MySQL. And of course, contrast this piece of software with the one we had on the Greek student network where it got integrated into the Radius. This is a standalone software. So for example, we can run it once per day or something like that. So some final slides before I finish. As you can see in both our cases, in both the cases I've shown you, we are storing offsets, non-negative integers instead of full prefixes in the directory. We are very happy with this decision because when indexed properly, we can get a very, very fast response from our relational database. So we are very happy with this choice. Like I said, in both cases, we use different prefix pools to group our subscribers, obviously. We use a relational database, and on the Greek school network case, which was the second case study, we use a database as a primary storage for the offsets, and then we copy the full prefixes in the directory. So if we were, if hypothetically we were to delete all the prefixes from the directory, we could recreate all the information from the database and store it again in the directory. I'll get to smash mapping shortly. And while developing this piece of software, it came about that the single user mode is equally as important as the batch mode because it really enables you to test the software in a sane way instead of having to run the batch mode each time. So some future directions that we're going to be taking, especially for the Greek school network case, which is still ongoing, we'd like to have the ability to add, and we'll probably do it some way, the ability to add triggers. So instead of having to use the software once per day, we could have external tools that are related with the creation and deletion of schools and units, able to trigger our software via an API, and then our software will come up with a prefix at the point of unit creation or deletion. Of course, in both cases, we are using offsets. So not only we can do IPv6 enumeration, but we could also do static IPv4 enumeration, quite possibly. At some points, our code needs some sort of cleanup. One remark that I'd like to make is that all these systems are they have the complexity that they get integrated inside Radius daemons, they talk to directories, they talk to databases, so it's easy to test the individual pieces of those pieces of software one by one, but it's actually very difficult to actually test the whole system as a whole. So the need for more rigorous testing is always there. And of course, there is documentation, but in an ideal world, I'd like to write much more documentation about it. Sparse allocation of offsets. As you've seen, we are allocating offsets, non-negative integers, one by one. So one idea that we've been toying with was like, instead of assigning the offsets in a linear fashion, meaning 0, then 1, then 2, then 3, and so on, we could allocate them in a fashion like 0, 0, then 4, then 2, then 6, and so on, in a modulo fashion. So this is described, and this is a very good practice, obviously, for higher levels of IPv6 address pools. But in our case, since we are doing the final level of offset allocation, obviously, after considerable offset recycling units or users will come and go all the time, our offset pool will anyway get fragmented. So doing the sparse allocation seems like it doesn't yield any results that I can identify as useful. So maybe we could be able to defragment, but I mean this would mean that the users will get assigned different prefixes. So this is okay, kind of defeats the whole purpose, if you ask me. So okay. So anyway, I think that we have like 5 minutes. Thank you very much for your attention, and I think that we can take a couple of questions. Thank you very much.
Any questions? Oh, sweet.
Okay.
Mike Joseph, Google. This is an interesting approach. Given your sparse allocation policy, I was wondering if you had considered something simple like hashing the username to determine the offset so that you could be relatively stateless in the radius server. You still probably would need to log it anyway for auditing, but it would mean that your use case, for example, where you were rebuilding LDAP from the database may become even easier because you would potentially reissue the same prefixes to the same user accounts, even across loss of all data.
Okay, it's very difficult to hear, but I think that you are asking whether hashing the username instead of trying to come up with completely random offsets per username is actually makes sense. Well, to be perfectly honest, that was the like 2 years ago or more. That was the initial idea that I have, and I mean it's the most obvious solution, and I agree with you. If there was a big enough IPv6 address pool, it could be conceivable that we could come up with a hash function. But you know, if we have very little bits available, eventually we will run into collisions.
It doesn't have to be collision proof, because as long as you have a collision rate that's relatively low, the majority of your users will still benefit from getting deterministic addresses, and the ones which do collide would simply then depend on state. So you would solve the problem nicely for the majority of your user base and reduce the churn, particularly on the prefix delegation, which is the hardest on customer networks because it means that devices on the LAN have to time out.
Perhaps. Yeah, okay. I mean, maybe
Just a thought.
Yeah, maybe we could discuss this further afterwards.
Sure. Thanks.
It's a nice. I mean, it's a valid idea. I mean, yeah.
Thank you.
Any other questions? Nope. Okay, well, thank you very much. Good job.